Oh yeah. Well, welcome. This is our online lecture. This is, hope you downloaded the PDF for the worksheet that goes along with this lecture. And it'll take, about the same amount of time as a regular lecture would take. I have my document camera, so let me move over there and I'll get started. Here's our worksheet. You should have, again, printed it. The homework for this worksheet is 6.3, 1, 2, 3, and 6. So you'll turn that in the week after we get back from break. I think it'll be Friday when we get back, I'm pretty sure. Okay, but we'll talk about that later. Okay, so let's get into what we're supposed to learn today, the Taylor series method. Suppose a function f has all derivatives at t0, then the Taylor series centered at t0 is, this is from Calc 2, you should remember this, but you may not have remembered it in this form. It looks the following: y of t is y of t0 plus y prime at t0 times t minus t0 plus y double prime at t0 over 2 factorial times t minus t0 squared. And this keeps going, y triple at t0 divided by 3 factorial t minus t0 cubed, and again this keeps going on forever. Now you might not have seen it in this form. You did it for probably a function called f with the independent variable x, but the idea is sort of the same here. I want to make some comments here. If t0 is equal to 0, well, t0 is called the center of this Taylor series. Okay, t0 is called the center. And if t0 is 0, it's also called the Maclaurin series. The series is called the Maclaurin series, just to remind you of some terms from earlier. Calc 2, called a Maclaurin series. That's not that important, just reminding you of some things from Calc 2. Some other cautions from Calc 2. First off, any series has issues possibly with convergence. So the series may or may not converge. This series may possibly diverge. And that's a whole issue that we talk about in Calc 2. We look at power series and we talk about when they converge and when they do not. You might remember there's the radius of convergence that we look at. And that's applicable here, but I'm not going to get too far into Calc 2 topics. So the series may or may not converge. It could possibly diverge. And the second warning about this method is even if the series converges, it may not it may not converge to y of t. Okay? And there's something called Taylor remainders that we looked at in Calc 2, and those are supposed to go to 0. I'm not going to get into all that in this class, of course, and all the nitty-gritty about Taylor series, but you can remind yourself that that was a fun experience in Calc 2. Okay? So all those issues about Taylor series come up when you're using it, this method. Okay, so I'm going to summarize this method before I use it. So here's the idea. We're first going to assume that our solution to our differential equation does have a Taylor series expansion centered at some center. And then we're going to find out what the coefficients are for this Taylor series by differentiating the differential equation repeatedly with respect to letter t, or whatever independent variable you're talking about. And then you're going to evaluate at t0. And then the other thing I want to make note of is that we are differentiating with respect to t, not y. That's a common misconception. So if you take a derivative with respect to y, you're actually getting dy dt. Or said differently, you can think of it as implicit differentiation with respect to letter t. Okay, usually we're not going to be able to see a pattern and stop, but we will stop at like a finite number of terms. Optimally, you would use like a computer package to generate lots and lots of these terms, but we're only going to do them by hand. So we're going to find out, enough terms for our examples. And fourthly, remember from Calc 2 that there's remainder theorems that you can use to your advantage. There's the Taylor series remainder theorem, and there's the alternating series test remainder theorem. These remainder theorems can be useful if you're trying to get some sort of precision, some guaranteed precision with accuracy for your solution to your differential equation. Again, I'm not going to talk about that. That's a Calc 2 topic. Okay? So let's actually do an example. I'm going to do example 1 here. We'll start off with this example. I've changed it a bit to be a little bit easier. Find the first 3 non-zero terms in a Taylor series solution for y double prime plus sine of y equals 0, with the initial conditions y of 0 equals pi over 4 and y prime of 0 equals 0. Okay, this differential equation actually does come up. It is the equation of motion for a pendulum or a swing. So it actually is an important differential equation. Okay, so let's see how this works. First off, our center, we want our center to be 0. So we're looking for a Maclaurin series. Now that's pretty much indicated by the differential equation initial conditions, because our initial conditions are specified at 0. So we want the center of our, we always want our center to coincide with whatever initial conditions we have. So in this case, our T0 is going to be 0. So we're looking for a Maclaurin series. And if you write out a Maclaurin series, Taylor series that's centered at 0 that way, it'll look like this. Y prime of 0 times t, remember T0 is 0, plus y double prime of 0, t squared over 2, plus y triple at 0, t cubed over 3 factorial, and then on it goes. Our job here is to find all these derivatives. Now you can sort of see what we want to do. We want to find y of 0, we want to find y prime of 0, we want to find y double prime of 0, etc. Infinitely many of those terms. Well, 2 of them have been given to us initially. That's our initial conditions. Y of 0 we already know is pi over 4. And we know y prime of 0 is 0. So we already have some a head start on solving this differential equation. So y of 0 is pi over 4, y prime of 0 is 0. Now, the directions say find 3 non-zero terms in the Taylor series solutions. We have 1. We have pi over 4. That goes right there. Okay? Now, how do we get the other ones? Well, as it said on the hint on the previous page, you're going to differentiate this differential equation with respect to t. Okay? But before I do that, I can actually use it without differentiating because I know y double prime is minus the sine of y. That's another way of writing that differential equation. And so I can use that to solve for y double. Y double at 0 is equal to minus the sine. Okay, here comes a mistake. You're not going to put 0 there. It says y. T is 0. So y is 0. So make sure you caught that. That's important. Okay, that's not 0. That is y of 0. And so y double prime at t equals 0 is negative the sine at y of 0, but that's given. That's pi over 4. You can sort of see how this is going to go down. This answer here then is minus the square root of 2 over 2. The sine of pi over 4 being the square root of 2 over 2. And so we've got that term, and we've got the y double prime of 0 term. Okay, so now we have to keep going, right? We want to find 3, I changed it, right? 3 non-zero terms in the Taylor series solution. Okay, so as I said, we have y double. How are you going to get at y triple? This would be a good question to ask if anybody were in attendance. Okay, so you take the derivative with respect to t of this. That's how we're going to get at y triple. Okay, so formally I'm just going to d dt both sides of this differential equation. On the left, of course, I get y triple. That's what I'm looking for, y triple. And on the right, I got to be careful because I'm taking a derivative with respect to t. So derivative of sine, yes, it's cosine, so it's minus the cosine of y. But I actually have a hidden chain rule or implicit differentiation to be dy dt there, or a y prime. So that's actually the third derivative for all t. Now, what is it when I plug in 0? Again, keep in mind I'm plugging 0 in for t. There's t there. Well, that would be minus the cosine of y of 0 again, right? Don't make that mistake of putting 0 there. Times y prime at 0. But I know y prime of 0 is 0, so this whole thing is going to be 0. That is 0, we already were given that. So y triple prime at 0, unfortunately for us, is 0. And so again, back up here, I've got that value, it's pi over 4. I've got that value of 0, so that'll go away. I've got this value, it's minus square root of 2 over 2, and now unfortunately that one's 0. Now again, the Taylor series goes on forever, so I need the next term. So I need to grab the next term, which would have been y to the 4th over here, y to the 4th at 0, t to the 4th over 4 factorial. So let's work on that. Okay, so we need y to the 4th. 1, 2, 3, 4. At some point, these tick marks aren't a good idea, but we'll keep going with that idea. Y to the 4th. Okay, and again, you get y to the 4th by taking a derivative of y to the 3rd. So we dt y to the 3rd, right? And that's equal to d dt of this business here. Now, I've got a product, so I've got to use the product rule. So let's use the product rule together with the chain rule. Okay? So derivative of cosine again is minus the sine. So that'll be sine of y times y prime. Times a y prime comes out from the chain rule. Okay, when I take a derivative of that with respect to t, yes, it's sine y, but again, I took a derivative with respect to t, so there's another y prime that pops out, and then of course there's this y prime. So that's my first product rule. I'll indicate that I use the product rule here together with the chain rule, because when I take a derivative of y, I get a dy dt out. Okay, plus leave the minus cosine y alone, and then take a derivative of y prime, but that's just y double prime. And that's our expression for y 4th derivative. Now again, we want to evaluate that at 0. So let's evaluate at 0, y the 4th derivative at 0. Well, this is going to go away again because I've got y prime at 0. I'll show it though. Y of 0 times y prime of 0 times y prime of 0. These are both 0. Minus cosine. Again, y is not 0. This is y of 0. So when t equals 0, again, y is pi over 4. Right, that's our initial condition way back up there. Okay, so this is actually pi over 4 times y double prime at 0, but we did that already. Y double prime of 0 was minus square root of 2 over 2. Okay, so like I said, this is going to go away. That's 0, that's 0. So we end up simply with cosine of pi over 4 minus square root of 2 over 2 times minus square root of 2 over 2, and that's simply a half. Now that actually gets me another term in my Taylor series. Okay, again, the next term that would have come here would have been y, the 4th derivative, evaluated at 0, t to the 4th over 4 factorial, and again, this would go on forever. But now we can plug into this, and we've got, finally, y of 0 equaling y of 0, let's see, y of 0 is pi over 4, plus y prime of 0, that was 0, t, plus y double prime of 0 was minus square root of 2 over 2. I need to divide that by 2. Oh, you can't see that. T squared plus 0. Y triple is 0, so it's y prime of 0. This is y double prime of 0 here. y triple at 0 we saw was 0. So I'm not going to continue writing the rest of that. Y to the 4th at 0 was not 0, it was a half. I need to divide by 4 factorial, multiplied by t to the 4th. Now again, oops, this isn't y of 0, it's y of t. Okay, it's y of t. So y of t now looks like this. Now, of course, it goes on forever. I've only found 4 terms. But again, you could use a computer package to fill out more and more of those. Okay? And get as many as you want, and as much precision as you want or need. All right, so that ends this. We've got 1, 2, 3 non-zero terms. Next example is as follows. We can also use this to find general solutions, okay, for a differential equation. Find the first 5 non-zero terms in a Taylor series general solution to y double prime plus y cubed equals sine t, centered at 0. And there's a hint here, let y of 0 equal c1, and y prime of 0 equals c2. So those are sort of your initial conditions. That will give us our general solution. Because you need 2 constants for a general solution for a second order differential equation. All right, well, let's write this down. So we've got y. We're looking for Taylor series solutions, so y of t. Here's the general form of that. Plus y prime of 0 times t plus y double prime of 0 t squared over 2 factorial. Again, the center is 0 again, so we don't have a t naught showing up in t minus t naught or something like that. Cubed over 3 factorial. Again, I'm going to need 1, 2, 3, 4, 5 of these. Take 1, 2, 4 of 0 over 4 factorial. T to the 4th plus dot, 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 dot. Okay? That's the form of the solution expanded as a Taylor series. Again, I know y of 0. Y of 0 is c1 now. And y prime of 0 is c2. So I know how this starts. I know that's that. I know that's that. We need to fill in the rest of these numbers. Okay, which we'll do below. Okay, so plus, coming up. Okay, so let's work on y double. Well, again, y double prime is equal to, well, plus y cubed is sine t. So we can solve that for y double. Y double is, let's see, sine t minus y cubed. Now, when I plug 0 in for t, y double prime at 0, I get sine of 0. Now I do have a t to evaluate. We didn't have that in the previous example. We do now. Minus y cubed. Well, again, that's y of 0 cubed. So it's not t. You don't plug t in there. You plug y of 0. But y of 0 is c1. So that's 0. This is minus c1 cubed. Again, because our initial condition was y of 0 equals c1. And so y double prime of 0, when you evaluate y cubed at t equals 0, you're going to get c1. So that's y double prime of 0. Well, let's keep going. We're going to need, as they said, 5 of these things. So let's keep going. And take a derivative now. Okay? So we had y double prime equals sine t minus y cubed. We need to dt both sides of this and see what happens. Again, we're taking a derivative with respect to t. Here we actually have some t's and some y's. In some sense, it's less confusing. Y triple is equal to derivative of sine cosine t. And then this, of course, is minus 3y squared times y prime. Okay, again, it's we're differentiating with respect to t. So from this, we can get y triple at 0 pretty easy. Y triple at 0 is equal to, well, cosine of 0 is 1. It's 1 minus 3 y squared. Well, y is c1. Y at 0 is c1. So remember, y at 0 is c1. So it'll be c1 squared. And then y prime at 0, okay, That's y prime of 0 is C2. That's what we call C2. So now we have an expression for y triple. So y triple looks like that. And again, we need one more term, so I got to take another derivative of this. d dt of y triple equaling cosine t minus 3y squared times y prime. Well, on the left, we get y to the fourth derivative. Derivative of cosine is minus the sine. And this we have to use a product rule again, so it's minus 6y times y prime, because I took a derivative of a y there, times y prime. Right, that's the derivative of that y came about from implicit differentiation. There's a multiplication there. Okay? And then leave the minus 3y squared alone, take a derivative of the y prime as a product rule, just times y double. Again, I'll indicate this was the product rule that we used to get from there to there. Okay, so now what do we got? Now we need to evaluate this at 0. Y to the fourth at 0. Well, that's 0. Sine is 0, 0. Sine is 0, 0. And then this stuff won't go away again. It'll be minus 6. Well, y at 0 is C1. Y prime at 0 is C2. So it'll be C2 squared. So we've got 2 of them. Multiply. Minus 3 C1 squared. And y double we found out was minus C1 cubed. And so believe it or not, you can keep going sort of forever. So let's see, y, 1, 2, 3, 4, 0 equals, I'll simplify this just a bit, minus C1, C2 cubed, squared. C1, C2 squared, minus 3, or plus 3 C1 to the fifth. Now again, I've got my constants, as many as I wanted 5 of them. So I'm going to fill that in. I'll put the full formula here again so you can see it. Y of t equals y naught plus y prime of 0 t plus y double 0 over 2 t squared plus y cubed 0 over 3 factorial t cubed plus y to the fourth 0 over 4 factorial t to the fourth, keeps going. Okay, so this was C1, this was C2, t, we had that before. This here was minus C1 cubed over 2t squared. We saw that earlier, that's y double prime at 0. Okay, y triple at 0, we found was this number. See it there. Okay, so let's fill that in. Plus 1 minus 3 C1 squared times C2, this whole quantity over 3 factorial t cubed, plus our last term that we'll fill in is this last number that we got, minus 6 C1 C2 squared, plus 3 C1 to the fifth, over 3 factorial t to the fourth. And this goes on. So as you can see, you're going to actually use this to find general solutions, or at least approximate general solutions. Because you've got your C1s and C2s here, which actually do make up your general solution. But we only found out 4 non-zero or 5 non-zero terms, so it's limited in what you can do without technology. It's not that great by hand. Okay, so that's how you can use this method still to get a general solution. Now, one example left to solve. So I want to solve this one. Oops, you can't see. There we are. Okay, we're going to solve this initial value problem. Y double prime plus 2ty prime plus y equals 3t. By the way, I should have said this. None of these differential equations could have been solved other ways. Not using methods we know yet. So you have to use a series approximation to solve these. For instance, this one is not constant coefficients. Second order, linear but not constant coefficients. Okay, so we're going to do the same silly method. The only thing that's different now is our T naught is 1. Our T naught is 1. Okay? And again, I'm going to write what the general solution would look like, what the general form of the solution would look like. Y of t will equal y of 1 now, we're centering it at 1. Okay? Plus y prime at 1 times t minus 1 plus y double prime at 1 over 2 factorial times t minus 1 squared plus y triple at 1 over 3 factorial t minus 1 cubed. Again, this goes on forever. Of course, we're not going to go on forever with this, although it seems like we have already. Okay, so y1. Okay, we know two numbers. We got y1 and we got y prime at 1. We need 1, 2, 3 more of these by taking derivatives. So I think you get the idea of what's going to happen next. I need y double solved, and I'm going to use the differential equation just to do that. So y double is minus 2ty prime minus y plus 3t. That's y double. That's just rearranging. And then so y double at 1, we can plug that in. Again, that's t, so be careful. Okay, that's t. Okay, and by the way, I know y of I should have written my initial conditions here. Y of 1 was 2, and y prime at 1 was also 2. They're the same. Okay, so from this information, we're supposed to get y double at 1. But again, that's t, so that's minus 2 times t, that's 1. Y prime at 1 is 2. So I put a 2 there, that's y prime at 1. Again, I'm evaluating y prime at 1. Minus y at 1, well that's 2. And then plus 3 times t, well that's just 1. 3 times t is 1. Well, t is 1. Okay, so this simplifies again. So we've got minus 4, minus 2, plus 3. I believe that's minus 3. Let's see if I did that right. Use 1. Oh, yeah, that looks good. Okay. So I got y double at 1. Again, I need 2 more terms. They wanted 2 more terms. Actually, again, formally you need infinitely many more terms, but I'm only going to do finite here, of course. Okay. So we ddt both sides. Here. Now we got y triple. That's what we get on ddt on the left. I got to use the product rule there again. Minus 2. Okay. Times 1 times y prime minus 2t left alone. The derivative with respect to t of the first derivative is the second derivative. And then this is just minus y prime. That's sort of easy. Plus 3. So this one's not as bad as what we looked at before. I'm going to evaluate that at 1. Y triple at 1 will equal, let's see, minus 2 y prime. Y prime at 1 was 2. Okay. 2t, so that's minus 2 times 1. T is 1. Y double, we found that out previous, it's negative 3. Minus y prime is 2. And add 3. All right, so let's see what we got here. We got negative 4. This is plus 6. Minus 2 plus 3. See if I can add. 9 minus 6. 3. Good? Good. That's y triple at 1. Now again, I need 1 more term. So I needed 4 and 5 they asked for. So again, we go through this process 1 more time. ddt both sides. To get at the 4th derivative, I'll keep that showing here. See right there. So we're ddt both sides of this. We get y the 4th derivative minus 2y double. Derivative of the first derivative is the second derivative with respect to t. Oh, got to use the product rule for that. Minus 2 y double minus 2t y triple. Minus y double, and the 3 goes away. So that's what I've got for the 4th derivative. And when we dump 1 in, so when t equals 1 again, we use our previous information. Again, y double at 1, we found that out earlier. That was negative 3. So that's going to be negative 2 times negative 3 minus 2, y double, again, came up. Okay, so negative 3. Plus 2, t is 1, y double, or sorry, y triple, that's 3. Minus y double, again, y double, so that's, let's see, what's y double? Y double was negative 3. All right, let's work out this stuff with the fourth derivative evaluated at 1. So I got 6, another 6, another 6, and another 3, plus 3. So, let's see, 6 is, what is it, 24, 21. Is that right? 1821. I believe. Let me double check. Let me double check. I'm double checking. Looks good. 2 times 1, whatever. Hold on a second. That should be a minus sign here. Let's see. That minus 2t. I differentiated that. Oh, I'm all right. No, I'm all right. Well, I just copied it wrong. That's a minus sign. Okay. So I copied a minus sign mistake. So aside from this minus sign here, it's 9. My students are used to this, right? Minus sign mistakes. Okay. So I failed to copy that minus sign there. All right, but anyway, there you have it. So now we've got all that we needed. We can fill in the rest, or we can fill in all of these that we want. We wanted 5 non-zero terms. Well, I've got 5. Okay, so let me fill in that formula. So y of t, I'll write the formula down again. It's y of 1 plus y prime at 1 times t plus y double prime at 1 over 2 t, oops, that's t minus 1. I should have just copied it. Plus y triple at 1 over 3 factorial t minus 1 cubed plus y to the fourth at 1 over 4 factorial t minus 1 fourth. And again, this goes on forever. But our solution is, when we plug this information that we found out in, 2 plus 2 times t minus 1, we already found y prime of 1, plus y double prime at 1 was negative 3, I believe. Yes, negative 3 halves. We had to divide by that 2 and 2 factorial in the Taylor formula. Y triple at 1 was 3. It's 3 over 4 factorial. T minus 1 cubed. Oops. That's 3 factorial. 4. And then plus y to the fourth at 1. Y to the fourth at 1 is 9 over 4 factorial t minus 1 to the fourth. And again, this would go on forever. But I think you get the idea that you just fill in these numbers using the Taylor series formula, and you're good to go. All right, and I'm good to go. This is the end of this crazy worksheet. Hope you had a good break, and we'll see you when we get back.